So today we're going to talk about how to draw Lewis structures for polyatomic ions, and then we're going to talk about something called resonance structures. And most of this stuff that we're going to talk about today is kind of a review of the things that we've already talked about, just one or two more things or wrinkles added to it. So moving on, you should remember your polyatomic ions. So at some point or another, you were told to write your polyatomic ions on the back of your periodic table. If you don't remember what they are, they look a little something like this. Nope, that's not it. Hold on. Let me get to the right spot here. That's it. They look like that. Okay. Now, you were told to write them on the back of your periodic table, but then we gave you a periodic table with them on the back. So some of you did and some of you didn't. So what's going to happen is that I'm going to, at the end of the hour, put this up for you to write them on there because some of you did, some of you didn't. But for now, we'll come back to that. You should definitely have time for that going forward. Now, all right, so polyatomic ions. Now, polyatomic ions should have been written on the back of your periodic table. I'll write that there just in case you forgot. And I will give you some time at the end of the hour to do that, but I will also post it on Google Classroom for you. But you have to remember that polyatomic ions are basically ions that are made up of a group of nonmetals that are covalently bonded together, and they have some type of a charge. So, for example, ammonium is NH4 plus 1, sulfate is SO4 minus 2, nitrate is NO3 minus 1. Now, the charge affects the electron bank or the electron pool or bucket, as I kind of think about it. Otherwise, everything else is the same. So let's talk about this for a second. The charge, if the charge is positive, like, for example, plus 1, you would be subtracting electrons. So you'd be subtracting electrons from the total. And if it's a negative charge, like 2 minus, you would be adding electrons to the total. The only other thing that's different about drawing Lewis structures for polyatomic ions is you have to put them in a bracket. So you take the whole structure and you wrap it in a bracket, and then you put like its charge next to it. So you have to put the drawn structure into a bracket. And then you have to make sure you have the charge. So that's really the only new thing that you have to worry about when we talk about drawing polyatomic ions. Everything else is pretty much the same. We count up the number of valence electrons that are available. We draw the central atom. We single bond everything if we can. And then we add electrons until we've used them all, and everybody's got 8. And then we put them in brackets, and then we give the charge that's associated with that polyatomic ion. So the next part of this is to do an example or two. And the example that we're going to do is ASO3 minus 3, which I believe is the arsenate ion, which is one of my favorites. So here we go. So in this case here, we have arsenic and we have oxygen. We know that we have one arsenic, and arsenic has 5 valence electrons and 3 oxygens. And we know from the periodic table that oxygen has 6 valence electrons, so that's 18 valence electrons. We add that together, what is that, 8 and it's 13, 23, right? Is that 23? 23 valence electrons. And then I see that there is a charge here of minus 3. So that tells me that I'm going to add 3 electrons to the total. So now I have 26 valence electrons to find a home for. So just like we've done in the past, I'm going to take my central atom, which in this case is the first atom. It's also the atom that, well, there's only one of them present. So I'm going to draw that in my middle. I'm going to add my oxygens to it. So I'm going to bond them around to the central atom. And then I'm going to do single bonds like so. And at this point, I've used 1, 2, 3 single bonds. Each single bond has 2 electrons in it, so 2, 4, 6. So I'm going to subtract 6 electrons from my total. So now I've got 20 valence electrons to find a home for. I start adding pairs of electrons to all of the other atoms until I've used up all 20. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Then I go back and I check to make sure that everything has 8. If I look at the oxygen on the right-hand side, the oxygen has one dash or one bond. That's 2 electrons and 6 dots, so that's 8 electrons. The oxygen on the bottom has a bond and 6 electrons, so that's 8 electrons. And the oxygen on the left, same thing. Arsenic has 3 bonds, 1, 2, 3, and which are 2, 4, 6 electrons plus the dots on top. That gives it 8. So each of these atoms has 8 valence electrons. So the last thing we need to do is put a bracket around the whole thing and write the charge of minus 3. So make sure that you're bracketing these, because if you don't, I have to take off points. The next example, ClO2 minus 1. So just like before, we're going to identify what we have. So I have chlorine and I have oxygen. In chlorine, there's 1 chlorine present times the 7 valence electrons that chlorine has in the periodic table. And so that's going to leave me with 7 valence electrons. I have 2 oxygens times 6 valence electrons, which would give me 12 valence electrons. And I add that up, and that's what? 19 valence electrons. I then make note of the fact that this polyatomic ion has a charge of minus 1. So I'm going to add 1 electron to the whole situation, and that's going to leave me with a total of 20 valence electrons to find a home for or replace. So just like before, I'm going to add my central atom to the middle, Cl, and to that I'm going to bond my oxygens, and then I'm going to start with single bonds. At this point, I've drawn 2 single bonds. Each single bond has 2, 4 electrons, so I'm going to subtract 4 from the whole thing, and that means that I'm left with, what is that, 16? Yeah, 16 valence electrons. So now I'm going to go and start adding electrons until I've used all 16. So as pairs, 1 or 2, 4, 6, 8, 10, 12, 14, 16. The oxygen on the right has one bond and 6 dots. That one bond is worth 2 electrons, so it has 8 electrons around it. The oxygen on the left has one bond worth 2 dots or 2 electrons and 6 dots, so that's 8 electrons. And the chlorine in the middle has 2 bonds. Each bond represents 2 4 electrons, and as a result of that, then the other 4 electrons on the chlorine give it 8. So in this case, all of the atoms are satisfied. So the last thing I need to do here is draw a bracket and put -1. Any questions about this? Okie dokie. The next thing we're going to talk about is something called resonance structures. And resonance structures are essentially the same thing, but you'll see why we have to talk about them separately. So the first thing that we have to do is we're going to draw the resonance structure for O3. And O3 happens to be the compound ozone, so it's kind of important. But we have oxygen. There's 3 of them, times the 6 valence electrons that oxygen has, which is 18 valence electrons. And so the very, very first thing I'm going to do is I'm going to draw, and it's hard because there's no technical central atom here, so I'm just going to link them all together to look like this. And when I link them all together, I'm going to put single bonds, and I'm going to note that each bond is 2 electrons, right? And 18 minus 4 electrons is, what is that, 14 valence electrons. So I'm going to start bonding or start adding pairs of electrons. So 2, 4, 6, 8, 10, 12, 14. So now I've added all of my electrons. And I can tell that the oxygen on the right has 6 dots in one line. One line is 2 electrons, so that adds up to 8. So oxygen on the right is good. Oxygen on the left has 6 dots in one line. So that one line is 2 electrons, so you add it up and you get 8. The oxygen in the middle has 2 dots and then 2 lines. So it's 2, 4, 6, so it doesn't have 8. So that means that in this instance, when you don't have enough electrons to get 8 for every atom, you end up adding a multiple bond by shifting one of these pairs. So in this case, I'm going to shift a pair over here. And I'm just going to redraw this structure off to the right with that shifted pair. So it's going to look something like this. So now in this case, the oxygen on the right has 2 bonds, 4 electrons, and 4 dots, 4 electrons. So that adds up to 8. Yes, ma'am. In this one, actually, no, we're not supposed to put brackets on this one because there's no charge. The ones up above had a charge, and those are the ones that get the brackets. Okay, yes?
So why do we move the dots to make a bracket?
We're not making a bracket. Oh, so in the first structure that I drew way over on the left-hand side, how it was drawn without the double bond, right? The oxygen in the middle only had 6 electrons, a pair of dots, and 2 lines.
So I could have taken dots from the other side if I wanted to.
Which is bringing me up to the next point. So hold that thought. So yes, some of you might be thinking to yourselves, well, what the heck? Does it matter? And the answer to that question is if I number the oxygens, in this case 1, 2, 3 from left to right, okay, it actually doesn't matter where you take the electrons from. But if I draw the exact same structure as you are thinking about in your head, with the multiple bond on the left side, in the structure, so at the middle, the one that I cleaned up, the first double bonded that I drew, the bond occurs between oxygen 2 and oxygen 3 when I counted from left to right. In the second structure I drew, the one all the way on the right, the bond occurs between oxygen 1 and oxygen 2. So technically speaking, they appear as though they are a different molecule, even though it just looks like we just moved the bond over one spot to the other side. So technically speaking, both of these structures are correct. And when both of those structures are correct, what we do is we draw a double-sided arrow indicating that for ozone, either of these is okay, but they both have to be represented. Now let me present you with some data to support this. We know that a single bond is longer than a double bond, is actually longer than a triple bond. Okay? But we've been able to measure that a single bond is 148 picometers long. So it's like this big. Okay? And a double bond is like 121 picometers long. So it's like this big. Okay? But the bonds in between in O3 are about 128. So they're not 148. They're not 121. They're like 128. So it's like right here in the middle. So the data suggests that the bonds in ozone are not a double bond and they're not a single bond. There's something in between. They're like a hybrid. Okay? So, and that's what a resonance structure is. A resonance structure is when you can draw multiple versions of the same structure. Okay, but when you draw those multiple versions of the same structure, neither of those versions actually exist because the bond itself is like this weird mashup of a single and a double bond. Does that make a little bit of sense? Yeah. So, as an example, we can draw 3 resonance structures for the polyatomic ion CO3-2, which is carbonate. So just like we've done before, I'm going to start with identifying what I have. I have carbon and I have oxygen. I know that I have 1 carbon atom times its 4 valence electrons. And I have 3 oxygen atoms times the 6 valence electrons, which is 18 valence electrons. And I add them up, and that's like, what, 22 valence electrons. And I see that I have a -2 charge, so I'm going to add 2 electrons to get a total of 24 valence electrons. So now I'm going to draw my structure. Okay. So I'm going to start with my carbon, and I'm going to bond my oxygens to it. And I'm going to do a single bond at first. And so of my single bond, I've used 2, 4, 6. So 24 minus 6 electrons is 18 valence electrons. I'm going to start placing electrons. So in pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18. Each oxygen is participating in 1 bond, so 2 electrons, and 6 dots, so 8 electrons. So each oxygen has the most stable arrangement of electrons it can have. Carbon, on the other hand, does not. Carbon is participating in 3 bonds only, and it only has 6. So we have to create, so this is an instance where we're going to create a multiple bond. So I'm going to grab 2 electrons and create a multiple bond here. So what I'm going to do is I'm going to redraw that structure down below. And I'm going to show the bonds and the electrons. And I'm going to show that there's a multiple bond, like so. And because it's a polyatomic ion, I'm going to put it in brackets and give it a -2 charge. But in this problem or this example, I'm telling you that there's 3 different ways we can draw this structure. And I'm hoping that you're guessing that each of those ways is a double bond on one of each of the oxygens. So my second potential structure will look like this. And I'll put it in brackets. And then there's a third structure, and I'm guessing that everybody out here is like screaming at me to draw it on the left, the double bond on the left oxygen. So we'll do that. Silent screaming. And because it's a polyatomic ion, I'm going to put it in brackets and give it a charge. And then because these are the 3 different ways we can draw this ion, we are going to put an arrow here. That is not a good arrow. There. 2 double-sided arrows indicating that each of these structures is a possibility.
So we have to draw all of them?
Yes. Questions? Okay. Your homework is to complete worksheet number 5, which I believe is a 2-sider.